Hello and welcome back. Let us try to understand more on statistical significance, p-value and hypothesis testing with two examples. The first example is there is an experiment, right? The experiment's outcome is that a smartphone can unlock by identifying human face when AI module is present. Generally accepted fact here is a smartphone cannot unlock by looking at a human face. So that is the null hypothesis. Historically accepted fact. From the day the smartphones were invented, the smartphone cannot be unlocked by showing your face to the phone. Right? That is the null hypothesis. The alternate hypothesis is opposite to null hypothesis. Smartphones can identify human beings or unlock by identifying human face when AI module is present. So here the p-value, the probability value we need to find is when null hypothesis is true, what is the probability of a smartphone unlocking by looking at a human's face? When null hypothesis is true, that means when AI module is not present, a smartphone able to identify human being's face is the p-value or the probability. So to do this experiment, what we need to do is we need to take a phone without AI module and try to show it to its owner, or we need to take 100 phones without AI module and try to show their owner's face to the phone. If the phones, out of 100 phones, if 5 or more are opening up or unlocking the phone screen, then there is no significance of AI module. Right? The probability here is out of 100, 6 phones. That means 0.6 is the probability. If the 0.6 times, if the experiment is happening true when the AI module is not present, then we say AI module is not significant. If it is less than that, we say the AI module is significant. Less than or equal to that, we will say the AI module is significant. Statisticians generally take 0.5 or 5% as the significance level, p-value significance level. The probability is significance level. Here the probability is when null hypothesis is true, whatever the observed result, how many times it is happening, that's the p-value. What is the observed result is here? The phone unlocking itself by identifying the human's face. That's the observed result. That cannot happen when AI module is not present. So if somebody says, or the null hypothesis says that AI module is not significant, then we need to do that experiment. When the AI modules are not present, we need to bring 100 phones and try to show their owners' faces and see how many times it is opening up. As far as our knowledge goes, 0 times it opens up because the AI module is not present. It is not going to open up. So the probability there is 0. The p-value is 0. That means the AI module is significant. We can reject the null hypothesis. We need to accept the alternate hypothesis. So if 2 phones opened up, then also we can reject the null hypothesis because the significance level is 5 here. If 5 times it opens up, even then we can accept the alternate hypothesis. It is less than or equal to 5. So more than 5, right? If 6 phones open up without AI module, the phone without AI module, it's opening up when you are showing the owner's face out of 100, right? Then you can accept the null hypothesis and say that the AI module is not significant. This is called as statistical significance test or hypothesis testing. Let's try to take another example and see and understand the p-value and the null hypothesis, alternate hypothesis and hypothesis testing. This time a little bigger example and a statistical problem. So there is a neurological stimuli which is injected to the drugs. Historically it is been injected and we are getting around 1.2 seconds of mean response time. The sample size is 100. Suppose that the neurological stimulus was invented in 1980. Suppose that. And from that 1980 till now, right, the researchers were taking 100 rats and injecting many 100 rat samples they are taking, injecting the neurological stimulus and taking the response time. Out of 100 rats, one rat may respond in 1.5 seconds, another rat may respond in 1 second, another rat may respond in 1.1 second. Like that, out of all the 100 rats response times, they have taken the mean that actually came as 1.2 seconds. Okay, so from history we know that when you take 100 rat sample and inject neurological stimulus, we are getting 1.2 seconds mean response time. A new researcher actually found a drug, and he or she injected that new drug along with the neurological stimulus to 100 rats. This is the new experiment. Along with the neurological stimulus, this person is injecting a new drug also. Now he recorded a mean response time of 0.05 with a standard deviation of 0.5. Okay, so the new person, he or she actually took 100 rats, injected neurological stimulus, and then the drug he or she invented actually injected that also. When he or she injected that neurological stimulus and the drug, the mean response time came as 0.05 with a standard deviation of 0.5. When I say mean response time is 1.05 and standard deviation 0.5, if the mean response time is normally distributed, 68% of the rats response time will be between 0.55 and 1.55. One standard deviation away. If the response times are normally distributed. When I say response times are normally distributed, I am taking response times on x-axis, counts on y-axis. If it is forming a bell curve, then we can say that 68% of the rats are responding between 0.55 seconds and 1.55 seconds. This is just to relate the normal distribution and whatever we are seeing here. Leave it. So in this problem, what we know is historically the mean response time of rats is 1.2 seconds. When the new drug is injected along with the neurological stimulus, the response time is 1.05 with a standard deviation of 0.5. That's the data we have. So we need to find, does the drug influence the response time? We need to find out whether the drug is significant or not. So here in this whole problem, what is historically known from 1980s? The mean response time is 1.2 seconds. Whatever is historically known is the null hypothesis. So here the null hypothesis is mean response time is 1.2 seconds. So to say that drug is, or to prove that drug is significant, the null hypothesis is actually saying historically accepted thing is true, right? So drug has got no effect. If you say the mean response time is 1.2 seconds or drug has no effect, it is one and the same. So the null hypothesis is historically accepted fact, and the alternate hypothesis, it is not equal to 1.2 seconds. It can be less, it can be more. So alternate hypothesis is always opposite to null hypothesis. Okay. So here the p-value we need to find out the significance, or the statistical significance can be measured with the p-value, right? So we need to find out the p-value. What is the p-value here? The probability of getting mean response time 1.05 seconds when no drug was injected, right? The p-value is getting the observed result. What is the observed result here? Mean of the response time is 1.5 seconds is the observed result. Mean response time, the new guy observed that it is 1.5 seconds. Getting the observed result when null hypothesis is true. What is the null hypothesis? Historically there is no new drug. Drug was not injected, right? When drug was not injected, getting 1.05 seconds probability, right? How many times 1.05 seconds response time is coming, that we need to find. Okay, to find that out, we need to take some assumptions and we need to bring out some data from our problem statement. So here the assumption we are making is, we know one sample standard deviation. When drug was injected, the sample mean response time is 1.05 seconds and the standard deviation is 0.5. Only one sample standard deviation we know. Now best estimation of the population standard deviation, we can take that as the population standard deviation. So we are assuming that population standard deviation is also 0.5 seconds. Okay, so that is one assumption. And we actually have to calculate the standard error. What is standard error? For a sampling distribution of means, if you calculate standard deviation using the formula sigma by square root of n, we call it as standard error. Right? To calculate the standard error, we may have to take these points, 0.1 to 0.4. We know that the mean response time is 1.2 seconds historically, or we are trying to find out the p-value, the probability value, right? The probability when null hypothesis is true, right? So when null hypothesis is true, the response time is 1.2 seconds. We know that from many samples and their means. From 1980 till now, there were many experiments conducted, and from all those experiments, we have seen means, and this must be the mean of all those means, right? In 1980, they must have conducted one experiment. Maybe it would have given 1.5 mean. Second one, 1.3. Third one, maybe 1.5. Fourth one, 1.1. Fifth one, maybe 1. Like that, 1,000 or 10,000 experiments would have been conducted, and we are talking about 1.2 as the one number, right? So out of all those 10,000 numbers, if you take mean, it's going to be 1.2 seconds. So it is actually sampling distribution of means mean, it is, right? This 1.2 seconds is sampling distributions means mean. From central limit theorem, we know that when you take many samples and take their means and try to look at the distribution, it's going to be normal. Right? The sampling distribution of means distribution is going to approach normal distribution from central limit theorem. Right? So this 1.2 is the mean of all the sampling distributions of means. So from central limit theorem, it follows normal distribution. Now if we know the standard deviation of this normal distribution, right, this is the graph. So we have taken many samples, and all those samples means we have taken on x-axis and try to plot, right, plot the distribution. We will get the normal distribution. We will definitely get the normal distribution from central limit theorem. So this is actually normally distributed, and we know the mean 1.2 seconds. If we know the standard deviation, we can find out in null hypothesis scenario how far this 1.05 seconds is from 1.2. Using that, we can calculate the probability, the p-value. So let's go back and try to see the standard error formula. The standard error can be calculated with sigma by square root of n. What is sigma here? 0.5 assumed, or best estimation of standard deviation, divided by the sample size is 100. 100 rats were taken. So it is 0.05 is the value. The standard error is 0.05. The mean of sampling distribution is 1.2. Standard error is always almost equal to the sampling distribution standard deviation, right? So we can subtract the standard deviation from mean and add standard deviation to the mean. That is one standard deviation away. So in this sampling distribution of means, what is this sampling distribution of means? We have conducted one experiment, took mean, conducted another experiment, took mean without drug, only neurological stimulus. We conducted an experiment and took mean like that. So all those samples, right? Out of all those samples, 68% of the samples means are between 1.15 and 1.25. How can I say that? It is one standard deviation away. The sampling distribution of means is normally distributed. In a normally distributed data set, 68% of the data is going to fall within one standard deviation, right? This is one standard deviation away. Mu minus sigma and mu plus sigma. What is sigma here? Standard error, 0.05. I subtracted and I added. So 68% of the samples means, 100 rat samples means, without drug injected is between 1.5 seconds to 1.25 seconds. 95% is going to be two standard deviations. So mu minus 2 into 0.05 and mu plus 2 into 0.05 is 1.10 and 1.30. 95% of the samples means are going to fall between 1.10 and 1.30. And 99.7% of the rats are going to fall between rat samples, 100 rat samples are going to fall between 1.05 and 1.35. So in the experiment, for the guy who injected the drug, he or she has got 1.05. That's actually 3 standard deviations away. When it is 3 standard deviations away, that means what? When the new drug was not injected, then also we were getting 1.05 and below response time also. Even 1 also we are getting, but it is very rare, right? Out of 99.7% of the times, when the drug was not injected, the rats were not responding that quickly, right? If you look at this diagram, you can assess that, right? 99.7% of the times it is not happening. How much percent of the time it is happening? Only 0.3% of the times it is happening. That means what? The p-value is 0.3 by 100. 0.003 is the p-value, or if you want to specify that as percentage, 0.3%. The statistical significance level for general experiments is 0.05. This is 0.003. It is very less when compared to 0.05. Hence, we can reject the null hypothesis. What is the null hypothesis here? The mean response time is 1.2 seconds, or there is no effect of drug. We can reject it. That means we can accept the alternate hypothesis. So, when we accept the alternate hypothesis, the drug has the effect. Because of the drug only, we have got 1.5 seconds mean response time. So that is about the how we calculate p-value and how exactly we do the statistical significance test. Before we end, let us try to understand what is two-tail test and left tail test and right tail test. Here we did a two-tail test. Now we are considering the probability on the left side and right side both. We have to do this because in the null hypothesis it is saying the mean response time is equal to 1.2 seconds. And we said on the alternate hypothesis, we said it is not equal to 1.2 seconds. That means it can be less than or it can be more than. So we need to consider both the probabilities. So we considered both the probabilities there. If the null hypothesis is saying if the null hypothesis is greater than 1.2 seconds, we would have considered less than or equal to. Then we would have considered only the left-tailed probability. Okay. If the null hypothesis is saying the mean response time is less than 1.2 seconds, we would have considered greater than or equal to on the alternate hypothesis. Then we would have considered the right side probability only. That is called as right tail test. So that's about the statistical significance and p-value. Let's try to understand Z statistic and T statistic, or Z score, T score, and where it should be used. So when you are handling population, you call that as Z score. When you are handling sample, we call it as T score. So when you are handling population, the variance is denoted with sigma square and standard deviation with sigma, and mean is denoted with mu. But when you are handling sample, you call variance with sigma s square and standard deviation as s, and mean can be represented with x bar or capital M. So the formulas are slightly different, right? The formula is all same, but only thing is the denominator is n minus 1 on the standard deviation or variance for the sample. And T score and Z score are same. We are trying to calculate the distance between the data point and mean in terms of standard deviation. Okay? When to take Z score and when to take T score. Do we have the population standard deviation? Yes. And if the sample size is greater than 30, we should take Z score. If population standard deviation is unknown, we will go with the T score. How big the sample, it doesn't matter. If you don't know the population and population standard deviation, you always go with T score or T statistic. The sample size, even though you know the population, standard deviation, and sample size is not greater than 30, then also you go with t-score. That's it. Thank you.